So, welcome to the last but definitely not least keynote of JuliaCon 2024. Our keynote speaker is a very important member of the Julia community, program chair of JuliaCon and applied scientist at Amazon. So I'm glad to introduce Katharine Hyatt, who will tell us why she uses Julia for quantum computing. Please join me in welcoming the speaker.
Thanks so much, Luca. So I have to confess, while I was preparing for my talk today, I was really confused because I kept seeing on the slides, Dr. Katharine Hyatt. And I was like, oh, I bet that person's talk is going to be really good, but I don't know who that is. Because even my own mother writes Christmas cards to me as Ms. Katharine. So I had a little bit of a struggle figuring out who exactly was giving this talk today. But hopefully, I'll be able to explain to you sort of the advantages of using Julia for a lot of different tasks in quantum computing, some of the things people today are thinking about, and opportunities for people in the community to contribute. So when we talk about quantum computing, we should be a little bit more specific about what exactly we mean. Because there's a lot of different things going on under the umbrella of the field we call quantum computing. So we can talk about using Julia for things like designing quantum devices, simulating those devices using classical computing. And then when we've actually built the device, trying to calibrate and control it using the microelectronics we need to actually make the device do what we want. And from there, we can also discuss things like constructs and algorithms for actually programming the device at a high level in a way that's sort of more feasible for human beings to read, write, and think about. We can think about problems that are probably pretty familiar to anybody who was watching the main stage talks over the past couple days. Things like IR lowering, figuring out the types of various objects, trying to translate constructs that are more familiar to us from classical computing back to quantum computing. And then sort of algorithmic implementations of things to control and deal with errors and noise. Again, anybody who's been watching talks here on the main stage for the past 3 days can probably understand the importance of dealing with noise. So that's something that we also really want to understand if there's a role for Julia for. And then finally, doing purely classical simulation of the quantum algorithms we'd like to run. So what I'd like to address in this talk is both what's already happening in the Julia community and what are the opportunities for us to contribute further. So what do we think of as Julia's strengths? Well, I think for this audience especially, this is the last keynote. I don't have to motivate this too much. We, of course, know that Julia is highly performant. It has great routines for linear algebra, numerical integration, PD solving. It's easy to compose tools from a variety of packages, which is great if you have a lot of different packages that are all working together in the same ecosystem. This means you don't have to constantly reinvent tooling necessarily. We have a strong ecosystem for probabilistic programming like Turing.jl. And what's also very important is that we have a really big community that's really happy to start working with early stage technologies where things are changing very quickly. And our community is really willing to adapt as things change over time. For example, when I started using Julia, my first Julia was like 0.4. If anybody remembers Array Apocalypse, that was a very sort of disruptive change, but it was for the better. And as Julia has evolved, we've also experienced these kind of pretty paradigmatic changes that kept the bones of the language intact, but we had to adapt to as we go. And I think this is a really big strength that we'll see called out throughout this talk that makes Julia a really great tool for this community. So 9 years ago in JuliaCon 2015 was my first talk. You can see there's a little screenshot there from the YouTube, and also the top picture from the hackathon that was the Saturday of that year. You might see some familiar faces in the picture of that hackathon. So at that time, I think there was like 1 or 2 quantum talks on the schedule. I confess I didn't actually go check the 2015 schedule. And now, 9 years later, the quantum community has really grown. We've had 20+ talks that are more or less about quantum computing, 2 keynotes that are pretty connected. It's the 2nd year of our mini symposium about quantum physics. We have multiple organizations that are supporting Julia developers in this area, both with like permanent positions and with micro grants. We have Julia code actively being used in industry to design devices. And most relevant to me, and luckily you can't really tell from the screenshot, I finally have gray hair. And I won't say whether this was caused by quantum computing or Julia. You can draw your own conclusions about that one. So since this talk is, fortunately or not, only 45 minutes long, and we have a lot to cover, I've added a couple icons here. So if you see this mortarboard, it means that this is actually a very complex topic, and many people have written a lot of PhD theses about it. So I'll try and include references that you can follow up at your leisure if you're interested, or find somebody at the hackathon for many of these topics that you can find out more about it. But in the interest of time, we're going to have to be brief. Presumably, you all don't want to be here until 3 in the morning. And then I've also included the little Julia icon if I think there's an opportunity for us to make a difference, or for us to sort of make inroads in a certain area based on the strengths of Julia that we all know and love so much. And again, just for the physics folks, since there's wonderfully quite a lot of you here, just keep in mind that the fact that we're going to have to go through quite a few areas means I can't cover yours in depth. So I apologize for that in advance. So I think one thing that's really motivating for me and a lot of people who are kind of working in this field is that, and this is a direct quote from someone who will go unnamed, we need scientists to be writing the prototypes that we use for this sort of early stage technology, but we also need the code to be really performant. And in a way, this is, to me, like a sentence that sums up the entire Julia community, where you have people who are both domain experts in whatever it is they're doing, like whether that's earth sciences or quantum chemistry, or even graphic design, but then they're also writing really performant code. So in effect, they're sort of, with their right hand, that's actually my left hand, whoops. With their right hand, they're doing their domain expertise, and with their left hand, they're also sort of getting a second software engineering degree, writing performant code. And this is something that Julia allows us to do relatively easily, and it's something very important for people who may be interested in coding, but what they really want to do is drive the field forward. So if we think about quantum computing today, maybe a rough analogy for where we are today is that we're kind of in the Cambrian era of this technology. So why did I pick this analogy? In the sort of Cambrian era of the evolution of life, we went from having like not that many different life forms. Again, I don't have a biology degree, so I'm sorry if I say something that's like a little off. And then in this era, we saw a complete explosion in the diversity of life. And I saw a nice quote that said that the major forms of sort of complex animal life emerged during this era. And today, we have a pretty diverse array of quantum hardware platforms that have emerged and people are actively working on, from photonics, trapped ions, neutral atoms, topological quantum computing, and the one we're going to talk about most today, which is superconducting qubits. So I don't mean that to say I think superconducting qubits are necessarily going to win, or they're best, or they're worst, or anything like that. It's just one example that I'm most familiar with that I think is sort of illustrative for the rest of the field. And the reason I think this caveat is important is if you somehow like time traveled to the Cambrian, or you look at fossils, you might say like, oh, like there's all these trilobites. Damn, these trilobites are doing really well. Like, there's so many of them everywhere. I bet these guys are going to have a really great run for the next, however many billion years on Earth. And they hung out for a long time. They did pretty well. But of course, today we know there's many other varieties of life, most of which aren't trilobites. So it's a little dangerous to over-index or over-rotate on what you're observing right now, rather than trying to look forward maybe at the large diversity of platforms we have coming on stage today. So with that, we're going to dive a little bit into the sort of device physics of superconducting qubits. So one thing I just really want to emphasize early on is that many of you have probably seen a picture like this one on the right. So this object on the right is a dilution fridge. And you'll often see in the media something like this picture on the right called a quantum computer. This object is not a computer. It's a fridge. The computer is the little chip on the left there that lives inside the fridge. That's where the computation happens. You need the fridge to make the computer work, but the fridge itself is not doing computing. It looks nice, which is why it makes a great piece for the media, but the fridge is not, it's essential, but it's not the same thing as the actual computer. So if you take one thing away from this talk, please let it be this. The object on the right is a fridge. And these fridges are really amazing because they manage to allow us to store a long-lived quantum state in a superconducting circuit. And when we actually cool these chips down, they're colder than basically open space. So open space, if you measure like the cosmic microwave background, is about 2.7 Kelvin. And the fridge is actually cooled to about like 10 millikelvin. So it's, I don't know how substantial the difference would feel to you, but to quantum objects, this difference is really significant. So this fridge, when it's working, is quite a bit colder than deep space. And inside, we have this little chip that is an engineered wafer. If you went to the ASML keynote, you may remember we were discussing wafers and semiconductors. So this is an etched wafer with some sort of photolithography, and it lives inside this fridge, and when it's cooled down, it can implement some kind of superconducting qubit. And there's many kinds of superconducting qubits. There's many different architectures. So even when we discuss superconducting qubits, just like the trilobites, there's actually many different varieties. And we're just going to discuss one of them quickly. But you should just keep in mind that there's actually a whole ecosystem, even in the what might seem like a relatively narrow area of superconducting qubit design. OK, so how does this chip actually work? So here is a relatively older, nice picture of a 4-qubit transmon device from IBM. So in this device, when it's cooled down, you have a bunch of electrons running around in the circuit. And those electrons get so cold, they pair up to form what are called Cooper pairs. So if you don't know what that is, completely fine. If you go on Wikipedia and look up BCS theory, you can learn all about what these silly little pairs are. But they only form at extremely low temperature. And in fact, for the computation to be effective, we have to cool the entire chip so much that these pairs are mostly in the qubit are mostly in the ground state. And that's why we need the really big fridge that we showed on the previous slide. So without the fridge, none of this works, and we can't do any computations. And then on the chip, you can see there's 4 little traps. And we make an idealization that within the trap, there's either 0 pairs or 1 pair. So that's called like a charge box qubit. And this transmon design that they have here actually does something even more sophisticated to make these pairs, or the states that represent 0 and 1, longer lived. But that's effectively the bare bones description of what's going on here. So we trap these little pairs in these 4 regions, and we can say there's either none of them or 1 of them. And that lets us do computations with them. And we manipulate them with the wires you can see on the outside of the chip. So we have all these wires that are connected to the external environment, and we send microwave pulses through the wires to control the device and do computation. Awesome. Wonderful. Now we're computing. Great. So this would be, we'd be ready to go, except, of course, when we're controlling the device, it's not isolated. So if the device were completely isolated and we never had to talk to it, these quantum states would be super long-lived. And everything would be great. But for us to do computations, we have to interact with the device by controlling it and then initializing it and reading it out. And this introduces a lot of potential for things to go wrong. So we're kind of trapped in this annoying dilemma where we want the device to be totally isolated up until the exact instant we want it to do something. And then it has to become unisolated. And then we need to isolate it again really quickly. So the entire sort of dilemma that we face when designing these devices is that we have a lot of trade-offs to make. So we have to draw a layout for these wires and these qubits. And then, again, as we saw in the wonderful ASML keynote yesterday, we have to actually create the chip, which is itself a very complicated process. Using that layout we drew, we put the chip in the fridge. Great. We cool it down. We run our workloads, see how good they are. Usually they're not so good. And then we improve steps 1 to 4 by gathering data. OK. So we're going to discuss steps 1 and 4, because those are the ones that are probably most relevant here. But if you want to know more about 2 and 3, or especially 2, you could probably find someone from one of our awesome sponsors, ASML, and learn more than you ever wanted to know about wafer deposition. So when we created a device layout, we have a bunch of trade-offs we have to make. And this is true, of course, in classical chip design, but it's true in quantum as well. So one of the big ones is the fridge we're thinking of has a fixed size, and it's really not very easy to expand it. So we got to get the chip to fit in the fridge die. And we want more qubits on the die, because that will let us do more computations. But we have to be able to address and control each one of those qubits. And the more components that are close together on the die, the more potential we have for quantum interference effects, for all kinds of errors to be introduced. So we have this odd sort of trade-off we have to make where we have something of fixed size, and we're trying to cram as much stuff into it as far apart as possible, in a rough sense, which is pretty problematic. And that's something that we can do computationally, and it's something where we need a lot of very high-performance simulations running quickly many times per day. So how do we actually do this? When we come up with the layout, we don't stand there waking up from a dream and just draw something, or maybe some people do. But usually what folks do is they say, okay, luckily, we've been studying electromagnetic physics for a long time. We have a pretty good idea of how both classical and quantum electromagnetism works. So what we'll do is we'll first draw some layout of the components we want on the chip, And then first we do a classical E&M simulation of the circuit, which has a bunch of nonlinear elements. So effectively here, you're doing some sort of finite element simulation, and there's a lot of nonlinear pieces that go in there. This is, as many people can tell you, a very computationally difficult problem. And for every single layout you want to do, you've got to do this first to make sure, as effectively a sanity check, like even without considering any quantum effects at all, is this feasible? And then once you've done that, okay, looks good. You do a Hamiltonian simulation that involves the sort of purely quantum physics that combines the classical results you got in the previous step with quantum effects. So just to shout out quickly to some of my colleagues, we, for example, have released a classical E&M software called Palace that you can check out, which is mostly written, I believe, in C++, but has Julia bindings that you can use to simulate device layouts like the one I've shown here, which has actually been fabricated. So what you can do is you can simulate first one unit cell of, you can see there's sort of a repeating pattern here. So you simulate one unit cell, okay, looks good. Then you simulate 2, and then 4, and then more of them until you run out, effectively, of ability to simulate this classically. Then you can go to the fabricator, fabricate it, put it in the fridge, and see how it does. But you need those classical steps to figure out whether it really makes sense to go to the fabrication step at all. And then you fabricated it, and again, if you want to know more about how that works, I suggest finding somebody from ASML. Okay, so we've done some fabrication. We have a chip. Now what? How do we actually control this device and make it do something useful? So it's stuck in the fridge is running, it's super cold. Okay, now what? So we're ready to run some experiments, and the way we do this is we actually have to send a bunch of low-level pulses to the device. So the device doesn't really have any notion of like our logic gates. You can't just walk up to the fridge and yell, do a C0 at it. You need to be able to control it using these sort of low-level continuous waveforms, and it's a very complicated problem in general to figure out the correct, or not correct necessarily, but best way to do that. You want something that will both be accurate, but then relatively quick to run, and then it's again a complicated trade-off at any time to figure out the correct sequence of pulses to keep the program and the chip running at acceptable quality. And so you also have to decide, like, okay, so I've run a bunch of experiments, and how frequently do I have to reset the entire device and recalibrate it between running various experiments or running people's workloads? This, again, is a complicated problem you can model computationally, and it's something that we actually have a lot of folks in the Julia community working on. Hopefully, some of them are still here. Okay, the device is calibrated. We've made our measurements. Awesome. And now our results look awful. What do we do? So we've run our quantum workload, for example, like some sort of Grover search, let's say, and we see something unexpected. The device quality is really bad. Very occasionally, we might see something better than we expect, but oftentimes it's worse, which is very sad for us. So we need classical simulation here, too, to understand what the cause might be of the device not performing as we expect. Because we did a bunch of simulation before we fabricated it that gave us some sense of, OK, we think the device will perform like this, and it's not, so what's going on? And we need a complicated physics model of each device component, and then we combine all of those and integrate a very oscillatory time-dependent PDE, which, again, as anybody who's worked with some of the Julia PDE integrators can tell you, this is not an easy problem to integrate one of these devices, especially in a performant way. And we need to use our results from this process to figure out what could be wrong with the device. Is it that our e-beam lithographer has something wrong with it, in which case all of our subsequent fabrications are not going to work, and we have to get somebody to come fix it? Is it that our pulses were bad, and that's why the results on this specific qubit don't look very good? Or is it that the design we came up with is bad for a reason we don't understand? We have to go back and consider whether we understand the physics of this component, or whether we modeled an incorrect approximation for some aspect of the design. And this may require doing some sort of open system integration using a Lombardian or master equation. And it's pretty difficult because factors even outside of the chip and the fridge can play a role in it. So for example, quantum computers like these really don't like having variable magnetic fields. So if you have the device in a building and somebody very occasionally is taking the elevator, the elevator has a big block of iron that's its counterweight often. And so very occasionally, if the elevator is going up and down, there's a variable magnetic field that can affect your device quality. And you need to figure out, is that what's causing this, or is it something else? Is it the device is bad, or I need to tell people to stop taking the elevator? Which one of those is maybe a harder problem to solve than the other one. And now, OK, so we've had the device fabricated, we've done some simulations, the quality looks good. So now we actually need a way to program this thing at a level that we can understand and we can devise algorithms for, which means we need a way to specify the actual workflows we want to run on the device. So we may have like a very high level construct here, like we have some input state, which I've drawn as psi here, some algorithm, for example, the quantum Fourier transform, and we want to get some output state from it. So again, how do we actually turn that into something we can run on the quantum computer? Because similarly to before, we can't just walk up to the fridge and yell at it, please do a quantum Fourier transform. It probably won't understand. So we need a way to communicate directly with the electronic components and say, we need to do this quantum Fourier transform in a way that's performant and more or less error resistant on your specific device layout. So just like in classical computing, we take each component of this and we sort of break it down into individual pieces. So for anyone who's taken like a CS class, maybe in like assembly language, or if you're familiar with instruction sets, this is effectively the same process where you have some complicated operation you want to perform, and you're breaking it down into, classically this might be opcodes, and in quantum computing, instead, you have a series of quantum gates that you apply to qubits in the circuit. So this is an idealized representation of what we're doing on the device. You might have noticed that there's like a lot of layers of idealizations in this process. So part of the challenge you face is you go from something high level like this that's super idealized, and you have to translate it down to something very device specific, which is a problem we're going to discuss in detail. So we have our input state. We initialize the device all in the 0 state, so like the lowest lying energy state. OK, we're ready to run our algorithm. So we have some operations we apply just to prepare the input state for our algorithm. This itself can be a complex process. And then we have some more operations that we apply to actually implement the algorithm, and then we make sure measurement at the end. Great. OK, so where do these operations come from? Like, what are these operations we're going to do, and how do we know how to write them down and how to translate them to something the actual physical device can understand? So when we talk about a quantum gate, we idealize the qubits in the device as having 2 orthogonal possible states, as we talked about before, 0 and 1. And so these gates are implementing a particular logic operation on qubits. And it can be on 1 qubit, 2 qubits, however many. And luckily for us, we can represent this process with probably, to people in the Julia community, relatively familiar complex linear algebra, everyone's favorite topic, matrix multiplication. So these quantum gates can implement operations that flip the qubits. They can rotate them around various axes in phase space. They can entangle them together so they can induce correlations between them. So there's a lot of different operations that they can apply. And we can combine these to end up with some more complicated algorithm that actually does something interesting for us. And a very crucial point here is that some of these gates are easier to implement on certain types of hardware than others. So when we take a high-level algorithm description like quantum Fourier transform, it may be the case that the actual gates we use are very dependent on the device or like the underlying hardware technology we're using. So here we have a 2-qubit state psi. If anybody here is a C user, don't at me. And then we have a gate, the XY gate. So this rotates the 2 qubits that psi is addressing. And we can write down its matrix representation here. And you can see this is going to rotate the 0, 1, and 1, 0 states. And we just matrix multiply, or in this case, matrix vector multiply xy times our input state. And we get the output state phi, which now has a rotation applied to it, but only on the 2 states 0, 1, 1, 0. So this is a relatively simple gate. And by combining these, we can end up with the full implementation of some algorithm like the quantum Fourier transform. OK, so that's great. But the fridge and the device we're talking to doesn't know anything about linear algebra. Like if you go up to it and then start yelling like, here's my matrix, it's still not going to be able to do anything. So you need a way to teach the device how to implement this operation using the microwave signals it actually understands. And And this is a problem that we need a lot of classical computing for. So we have 2 qubits, and we have some gate, this XY gate that we want to implement. And the question is, what's the best pulse to send over the wires into the device to actually implement this gate? And there's lots of different techniques folks are using to try and figure this out. One example is you can use reinforcement learning to try and understand this. And unfortunately, or fortunately for you, the answer to this question can actually change over time as the device is running. So the gate pulse you run when the device first turns on at the start of the day might not be optimal 6 hours later. So then the question you have to ask is it worth it to use a pulse that's like kind of raggedy and out of date, or spend a bunch of time recalibrating the device and then figure out a new set of good pulses for it? And this trade-off, again, is not super obvious what to do. But generating these pulses and determining their optimal form is something we can, and many people are, using advanced classical computing techniques for. And if you want to know more about that, I definitely suggest hitting up the piccolo.jl folks, whom, again, may still be here. And so we have a lot of work to do still to figure out how do we turn this linear algebra representation that's like relatively understandable by humans into an optimal set of pulses in a reasonably short time frame for the device. And of course, if we're looking at this, you might say also like, you know, like linear algebra is okay, but I don't really want to write down all these matrices all day. Like this is kind of annoying. Even if you're one of those weird people like me who kind of likes linear algebra, like writing down a lot of matrices like this and multiplying them is like, am I really doing this? Am I back in undergrad? Isn't there some kind of higher level, like, you know, in classical computing, you can write down a bunch of truth tables and do effectively like a similar process, but we don't do that. We write down instructions, and then there's a whole set of compiler steps that turns that into something the computer can understand, and we don't have to worry about it. So can we come up with something like that for quantum computing? And similarly to sort of the situation in the hardware ecosystem where we have the emergence of many different options, we also have the emergence in kind of the programming construct space of several different intermediate representations for quantum programs. So we take some high-level circuit, like the one I showed with the psi, quantum Fourier transform, and output state, and we want to lower it to some kind of IR. Or maybe we want to take the IR and parse it back into one of those high-level representations. Like if somebody comes to you and they say, I have an IR for this circuit. Can you turn it into a Julia object for me, and then I'll try and manipulate it and compute some gradients on it. You need a way to take that IR and parse it, which means you need a lot of information about the IR, what are acceptable symbols, and things like that. And especially for the lowering step, you need a lot of device-specific information, because if you take your high-level circuit and you lower it to operations that are very hard to implement on the quantum computer, you're going to end up with a circuit that doesn't run very well. So you need a lot of up-to-date, current information about the device to do this lowering process in an efficient way that generates effectively good sets of instructions to then send to the pulse generator that goes to the device. So there's quite a few different IRs that are in use today. Probably the 2 most common ones right now, I would say, are OpenQASM 3, which is open source and come up with by a collective, and then QIR. And then just to plug a project of mine, so I recently open sourced this new package called quasar.jl. It's actually a submodule right now. But it's a purely Julia OpenQASM parser based on Automa. And if you know the open pulse grammar really well, come talk to me at the hackathon, because we need these kind of constructs to enable the Julia community to be able to quickly work with these kinds of IRs, be able to translate back and forth, and make use of the higher level constructs we have and the lower level packages that, for example, generate these pulses. Okay, so what does it actually look like when we represent some quantum program like this? So we have some OpenQASM file here. Probably many of you looking at this can guess what language this might have been inspired by. The def is pretty telling. So if you wanted to write a program to run on some quantum device, it could look like this. You have a header that says, like, hey, I'm an OpenQASM program, and here's my version. And then you define some functions. You have a function bell that operates on 2 qubits and applies some gates to them, and it generates a bell pair. So this is a relatively basic quantum circuit. It's one of the things you got to be able to get right before you get anything else right. So this bell function entangles qubit Q0 and Q1, whatever those are that you pass to it. And then we have another function, nbells, that, and this will shock you, it applies this bell entangling procedure multiple times to the qubits. The indexing here might also tell you where they drew some inspiration from. And then we have a bunch of variable declarations that say, like, okay, this circuit runs on 4 qubits. We're going to entangle qubit 0 and qubit 1. And then we're going to run this bell generation procedure 5 times on qubits 2 and 3. And finally, we make some measurements just to see what the output state is. And that will be the result of our circuit. And then, of course, the device takes this file and turns it into the pulses for us. But the goal is, if we want, we can specify this pulses. But if we don't, we can just say, like, all right, I trust whoever programmed this device to have some decent pulses set up for me. So I'll just give it this thing, and it'll run it. Awesome. So under the hood, what's actually happening from this sort of linear algebra construct point of view is we have an input state psi up there, and we're going to apply this bell function. So we have this H gate and this controlled NOT gate, which is effectively a flipper on Q1. And if we actually write out the matrix formula for this, we can see that the first gate we apply has this form. It's just this little 4x4 matrix here. And the C NOT, which is a controlled NOT, has the form I've shown here. And we can actually just multiply these together to get a unitary matrix that represents the entire circuit. Hurrah! So it's relatively easy to see for a small 2-qubit circuit like this what the matrix form of the entire circuit operation would be. And from there, you can generate all your truth tables and everything we love so much from classical CSC. OK, so now we want to consider what happens if there's one other qubit that we have to worry about. For example, when we start applying gates to qubit 2. So then we need to consider the states on qubits 0, 1, and 2. And on each of those, there's 2 possible states, 0 and 1. So the total length of the state vector is 8. And it means the operation of that first gate is now an 8x8 object. And so each additional qubit that we include in this problem increases the size of the matrix we have to consider by a factor of 2. So generating the entire circuit unitary very quickly becomes infeasible, which is part of why, even if you don't care about the pulses, these kinds of intermediate representations using these, if you like, quantum DSLs are really important for us. We need a way to, instead of having to write like a 2 to the n by 2 to the n matrix to specify our program, we just want some human-readable instructions. And coming up with a good set of these is not necessarily a trivial problem. And then from there, we can go all the way even higher to these sort of diagrammatic representations and start building something that we can actually like pass into an auto-differentiation library if we want. OK. So if we start chaining together all these abstractions, we can end up with what's effectively a relatively robust pipeline that goes from, I want to run some algorithm that I heard about from some quantum textbook, all the way down to the pulse level. And we can even stack things on top, like computing gradients with autodiff, making optimizations for measurements, making mid-circuit measurements so we can do control flow. And the result of this is that one program that we want to run on the device may become many thousands of these open chasm instruction sets. And even worse, we might need to compile the instructions to take advantage of specific features of the device. For example, when we do our calibration, we see that some qubits are working better than others, so let's focus on running our stuff on those. And as many of you no doubt know, we have this amazing community package, yao.jl, that's really more of an ecosystem that allows us to do a lot of this kind of work. And so just to kind of elaborate a little bit more, and specifically in the superconducting qubit context, this is really important because not all of the qubits are connected. So if you are familiar with classical HPC, this probably isn't that unfamiliar because, of course, often when we're running on a classical cluster, not all of the nodes in the HPC cluster are connected to one another. So your algorithm's performance can be really degraded if you don't take into account the specific topology of the cluster. And it's exactly the same for a system like this, where not all the qubits are all connected. The reason for this is that the devices, when they're created, have a definite layout. And so we need to consider, how do we apply a gate on 2 qubits, like the one in red and the one in purple here I've shown, that are not directly connected? So we may have to decompose the operation we want to apply between these two into many intermediate gates. And you also then need to pick a path to apply those gates through the layout of the device, taking into account the specific fidelities, or if those qubits are supposed to be running other gates at the same time. And so it's effectively a large graph problem, which again, I hear that there's a language out there that has really good libraries for this kind of weighted graph optimization. If anybody knows about it, please let us know. And there's even more complex and irritating problems we have to solve. Like, for example, if the device has a lot more qubits than the circuit, which qubits should we pick to run the circuit on? Picking a good embedding in the device can, again, drastically affect the quality of our results. And we also might need to consider, let's suppose we fabricate 3 of these chips that have a small number of qubits, but we want to run a really big circuit. Is there a way we can do that by effectively chopping up the circuit into pieces and sharing information between our chips? And so this problem is also probably relatively familiar to people coming from an HPC world, but the different latency between the devices presents a really big problem for this, and we have a lot of work to do to understand how can we use compilation and our understanding of sort of the layout and the current properties of the device to compile the algorithm we want to run into something that the device can actually do. And even worse, the devices are subject to noise. So the devices that we use every day, like our phones and like our classical computers, of course, are also subject to errors. For better or worse, they've been around for a long time, and we've gotten really good at classical error correction. So we often don't think about the fact, like, if you've ever used a GPU, you might have some like ECC, which is for the error correcting code on the GPU, turned on, and it's like, okay, I don't know what that is. I'm not going to worry about it. But unfortunately, the quantum devices that we're using today are subject to a lot of errors, and it's partly a result of the fact that we want them to do things. If they were perfectly isolated, we wouldn't have these problems, but they can't be because we need to give them instructions. And so there's various types of error that can exist. So for example, we have here like a sort of cartoon diagram where we have the 0 state of the qubit is the lowest energy state, so that's why it's on the bottom. And then the 1 state is higher energy, which is why it's on the top. And so we've prepared our qubit in the 1 state. That's great. It's hanging out. It's having a good time. And then it decides, you know what? I actually want to go down to my lowest energy state, because nature usually would prefer that I do that. So it's just like, all right, bye. I'm emitting a photon, and I'm going down to the 0 state. And it did that without your permission. You wanted it to stay in the 1 state, but it's not. It's in the 0 state. And there's really, you can't prevent it from doing this. Nature is just like, okay, see ya, I'm emitting my photon now. And this is called like the T1 relaxation time, and making this longer is a very important part of making these devices more usable, because it reduces the error rate. Because you were counting on this guy being in the 1, but he's in the 0, completely, without asking you, which is very rude. And even worse, there's other errors that these little qubits can experience. For example, they can have their phase rotated without your permission. So we can have a qubit that starts out in the 1 state, and it doesn't have any particular rotation, or maybe a slight one in one direction. And then, without your permission, it has an interaction with another qubit and completely flips its phase. And this is a problem for us because many of the algorithms we want to use actually require these qubits to have certain relative phases to one another as we perform the algorithm. So if one of them gets rotated, again, completely without asking us and without our permission, it can affect the quality of our results pretty severely. And another common problem that we can encounter is, we have 2 qubits, let's say one in the 1 state and one in the 0 state, and we want to apply some gate to them like controlled not. So we want to control on the first qubit being in 1. If it is, we're going to bring the second qubit up into the 1 state too. We're not going to rotate anybody. And 99% of the time we do that, it works great. Awesome. Love that for us. But occasionally, when we apply the gate we intend to apply, we get a ride-along where we unintentionally apply some other gates, perhaps because the pulses we applied weren't very good. Or, some theorist walked into the room and they had a magnet in their pocket or something like that. Of course, I would never do this, but things like that can happen. And we ended up with multi-qubit errors where not only are these guys both in the wrong state, but they're also phase rotated. And we need some way to either prevent this from happening, notice it's happened, or at least be able to adjust our results to take into account that it's happened. And even worse, and you probably are going to get tired of hearing this refrain, different devices can have different noise profiles. So even if, let's say, you have a really great layout, like it's the world's most awesome layout to date, super good, and you fabricate it 5 times, then you'll still have 5 different noise profiles for that device, just based on very slight differences in the way it was fabricated and the conditions it's experiencing in the fridge. And so for each chip you have, you need to come up with an effective noise profile for it that, of course, is informed by your understanding of the device physics, and then correct for these kinds of errors as they're occurring in the device, which is a pretty hard problem. And just to kind of illustrate how important this is, we often characterize the circuits or algorithms we want to run in terms of the number of these 2-qubit controlled NOT gates we need. The reason for this is that if we have an error rate of 10 to the minus 4, so 99.99% of the time it's successful, we want to understand how many gates can we run before the results effectively become just a lot of noise. So having results that are effectively noise is great if you want to generate a lot of random numbers. Like generating random numbers is cool, but if you want something that's not a bunch of random noise, even a 10 to the minus 4 error rate can cause big problems very quickly. So I have drawn this histogram with a more exaggerated error rate, just to kind of show how this can accumulate even for one gate. So with no noise, you have the idealized result in blue, and then with a 10% error rate, if you run 1,000 shots, you have the results shown in orange, and with a 15% error rate in green. And so you can work out, if I accumulate errors at a 10 to the minus 4 rate, and my circuit needs 10 to the 6 of these controlled NOT gates, it's probably not going to be very good for my output, right? 10 to the minus 4 times 10 to the 6 is not a happy number if that's the total amount of error you've accumulated. And this is a big problem because the devices we have today, despite a huge amount of engineering effort that's been super successful by a number of very smart people, much smarter than me, this is still kind of one of the barriers we're encountering when we try and run these 2-qubit gates. So a lot of the algorithms we rely on really need a lot of these CNOTs, more than 10 to the 6. It can be up to like 10 to the 10 or 10 to the 13. So just running these on physical qubits, even ones that are pretty high fidelity rates, is going to quickly become very frustrating for us. And we need a way to deal with this. So of course, in the ideal world, what we would do is just say, it's illegal to experience errors, so you can't do it. Again, I didn't consent to this qubit flipping, so just don't. Unfortunately, again, if you just go up to the fridge and you yell at it, like, stop flipping, it's not going to listen. So we need a way to cope with a world with a lot of noise in it, which again, probably this week, many of us have a lot of experience doing. Although it seems that now the noise has been mitigated a little bit, which is good. So we have a bunch of different approaches we can take to dealing with the noise that the device experiences. We can try and mitigate the effect of the error. So we have lots of different algorithmic techniques we can use to handle these errors. We can try and infer a probability distribution, and then use that to adjust our results. We can suppress the error with a real-time adjustment of our pulses. This is, again, a super complicated problem that needs a lot of high-performance, low-latency classical compute. If only there were a language that were able to do that. And then kind of the ultimate goal for us is to be able to correct the errors so that we can run lots of circuits that have lots of gates for a long time without having to run a huge number of duplicates to effectively back out what the error was. And so the way we're interested in doing this is using what's called an error-correcting code. We construct a logical qubit that is an overlap of many physical qubits, and it allows us to detect and correct the errors. And this is something that needs a lot of low-latency classical control. And one very popular approach for superconducting devices is the surface code. So in the interest of time, I won't be able to go super in-depth into how this works, but I encourage you to check out this paper by Austin Fowler et al. It's a really great introduction for people with mathematical background, but not a lot of physics intuition necessarily. And our goal is to effectively create a bunch of tiles over the physical qubits that then create a logical qubit. And the number of qubits we need in each tile depends on both the physical qubit's error rate and the desired error rate of the logical qubit. So if the physical qubits we have are really noisy, we need a lot of them to get the logical error rate down, which is why it's still valuable to work on lowering the error rate of the physical qubits. And the implementation of these is, again, controlled completely classically. And this is something we can both implement at the microcontroller level when we talk to the device, and it's something we can simulate classically. So this is great. There's a lot of progress being made on implementing these. But unfortunately, it's still not enough. The problem is that these devices are still subject to not just errors, but defects. So what's the difference? Errors are relatively uniform, which means if we observe the error rate being like 0.1 now, and I go out for a coffee and I come back later, the error rate's probably going to still be about 0.1, and it's relatively evenly distributed through the device. They're relatively low magnitude, and the accumulation rate is quite low. And the whole point of an error-correcting code is to detect and correct errors. Awesome. But defects are not uniform, both in space and time. They're pretty rare, but when they occur, they're really bad. They're really difficult to detect, and they can't be corrected by existing sort of vanilla error-correcting codes. So one variety of these is called static defects. That's what we already discussed with device or calibration manufacturing errors, or they can be dynamic. And these ones are pretty interesting because they are often caused by cosmic rays. So these are high-energy particles coming at us from space. Luckily, we live on planet Earth that has both a very thick atmosphere and a magnetosphere, so we have like a nice blanket protecting us from quantum defects, which is great. The Earth is trying to make quantum computing happen, which is wonderful. Thank you, planet Earth. But these defects still affect the devices that we are building, to the point where if you actually take one of these quantum computers and put it in a deep salt mine, you'll notice that the accuracy of your computation actually goes up because it's no longer being bombarded by cosmic rays. So that's not really practical. Like, probably most of us working on these devices don't want to work in a salt mine 3 miles under the ground. So can we come up with a sort of improvement to our error-correcting codes using classical software that allows us to heal these sort of point defects? And there's a lot of kind of cutting-edge work happening in this field right now. I've included some QR codes for it. And here's a nice diagram from one of these papers about the entire sort of flow of these algorithms where you have defects on top of your existing errors, and you need to detect them, handle it in your error-correcting code, and continue with your computation. We can't go into all the details right now, but as you can see, there's a lot of complex classical computation that has to happen very fast and low latency in here. So, of course, there's many options for how to do that. It's not guaranteed that Julia is the only one or the right one, but I think there are a lot of opportunities in this whole space for the Julia language and Julia users to contribute to kind of these developments. And then finally, this is sort of the area that I actually am most familiar with. We need to compare with something to understand whether our quantum computations are working. So we want to both simulate quantum algorithms themselves and then simulate the systems we want to study with those algorithms. When we say that quantum computers are useful, we have to compare with the classical state of the art. And the only way to find out what the classical state of the art is to do classical computing. So even if you don't know very much about quantum computing, there's a huge contribution to be made improving the performance of the classical algorithms that already exist. And so one of the big applications people are interested in, though of course not the only one, is doing quantum chemistry with quantum computers. A molecule, as we saw on Monday, is basically a big collection of interacting quantum objects. There's a lot of nuclei and electrons running around. These are quantum particles, and quantum mechanics governs their behavior. So you want to figure out what geometry is nature going to favor, and can you understand if or when reactions are going to occur. So there's a lot of sort of proposed applications for this, from doing carbon capture to studying things with aromatic rings. And one thing that's really great about doing quantum chemistry is that human beings have been doing classical computational chemistry for a really long time. We're really good at it, which is good. We have made a lot of progress in the world because we're good at doing classical computational chemistry. So it's pretty hard for quantum computers to beat, for a lot of systems, the classical state of the art, which is a good problem to have. But for some systems, the exponential blow-up we see is just so bad that classical computers find it really hard to make progress. So in the presence of strong interactions, these classical techniques break down. And we need, we think, some kind of quantum computer to compensate. The way we do this, and I'm going to have to breeze through some of these in the interest of time, and I think there are drinks after this, so I'll try and be quick, is we need to translate a continuous system that represents the position of all the electrons into something digital that we can actually run on the quantum device. doing this translation is a really complicated classical computational problem. Again, this is probably a phrase you're tired of hearing me say. And this is also a really big opportunity for the Julia community. Many of the codes that do this now are great, but they're Python wrappers sitting on top of C++, a problem many of us got really sick of dealing with and wanted to avoid. And so there's a lot of low-hanging fruit in this space to implement both existing algorithms for doing these kind of translations and coming up with new ones. And then we also want to understand how we can take the existing quantum algorithms that we have come up with as guesswork for trying to use these and improve them. There's a lot of quantum algorithms out there for electronic structure or molecular geometry that we would like to run, but they have pretty bad scaling problems. So the naive version of the unitary coupled cluster ansatz, which is the one most of us use for quantum chemistry, has n to the 8 scaling. So n to the 8 is better than 2 to the n, but it's still really bad. And we haven't even talked about the prefactors. So what we would like to do is use a bunch of these algorithmic techniques, which many people are working on, to cut down that n to the 8. There's a lot of progress being made here, but it won't shock you to hear a huge amount of this relies on high-performance classical simulation of these systems. And this is something where we need a lot more of this simulation to understand how these algorithms compare with each other and how they compare with the quantum state-of-the-art. Or we need a lot of ways to efficiently generate these quantum circuits. And again, in the interest of time, I'll get to the part that probably many of you came to this talk to see. The question of integer factoring. This is the application of quantum computing that many people are very interested in, although a lot of physicists are tired of hearing about it because we don't care about integers. So I'll just say, here's a beautiful integer on the left, and here's 2 primes that I looked up earlier today that claim to be primes, so I believe them. So if you want to factor this object on the left, the claim is you can use a quantum computer to do it with some speed up. The good news is, to do this, you need on the order of 1,000 logical qubits, and today we have about 1. And the engineering task, as I've hopefully convinced you in this talk, of getting from 1 to 1,000 is pretty complex. So I wouldn't worry about it this year. And hopefully, by the time someone is giving another quantum computing talk, we'll have a better idea of how long this is going to take. But in the meantime, there's a lot of really interesting challenges that we want to tackle and that we can use Julia, I think, to make a huge amount of progress on. And we can have fun doing it, which is always a good problem to have. And I think there's lots of opportunities today to contribute at all levels, like even in completely classical computing, if you're like, oh man, this is awful, like this quantum computing stuff you've convinced me is terrible and I don't want to talk to these devices. That's great. You can use classical computing to prove that they still don't work for many problems, which is a good thing for people to be doing. And I also just want to emphasize that we can't assume quantum computing will evolve as classical computing did. Of course, in hindsight, it's obvious to say, like, yeah, the transistor came on the scene and that was it. And now classical computing is all based on these specific microarchitectures, and therefore quantum computing will be the same way. But we don't know that that's the case. So there's still a lot of growth in the field left, and we don't want to assume that everything is going to stay a trilobite. And finally, I just want to say that over the past 9 years, the Julia quantum community has really grown, and now we have all these amazing packages, including any I forgot. And hopefully, the next time I or someone else is giving a talk like this, we'll need a lot of slides to show all the packages we have. Many of these folks will be here during the hackathon. And finally, since I'm definitely over time, thanks everyone for your attention, and hopefully, we'll see more of you in the quantum community soon. Sorry.
Thank you very much for the great talk. Do we have questions from the audience?
Yes, sorry. People in the balcony, you also can ask questions.
Oh, wow, they really came prepared.
There's one question on the second floor, here on the left. So if we can get the catch box on the second floor.
What's that? Nice.
Someone want to ask a question here?
See, that's a great example of a 2-qubit error. Right
Looks like we're actually doing sports in the stadium here. So my question was, considering that you need a lot of classical computing to even control these qubits, shaping your pose, etc., at what kind of problem size do you expect that the classical computing that we need to do in order to control these qubits is even viable to get some computing benefits out of the quantum qubits?
Yeah, it's an interesting question, partly because it's a moving target. So having to do these pulse optimizations repeatedly is partly an artifact of the fact that the devices we have, let's say they have room to grow. So as the device improves and as we better understand how to control it, you have to do fewer and fewer of these adjustments to control. To kind of control what the device is doing. So, early devices are kind of like a waterbed, right? Like you jump on it and then it sinks where you are and it goes up everywhere else. And you're rolling around and it's sloshing and it's just very hard to control what it's doing. Again, this is like a very rough analogy. But the devices that we're working on building now are much more controlled, where you like press on it on one spot and it doesn't, floof up somewhere else. So we have a much better ability to keep the device in a relatively kind of static state, which then reduces the need for constant recomputation of both the pulses and then understanding of what the device specifically is doing.
Thank you for the very nice presentation. My next question is, can AWS bracket simulator do weak or strong simulation, and how many qubits is the max?
Sorry, could you just clarify for the audience what you mean by weak or strong?
Sometimes our question.
If you have strong simulation, you get the complete state vector, and the weak does not. So.
Yep. For those who don't know, Bracket Simulator is a package we just launched that lets you do simulations of these systems on Amazon Bracket. It has support for both full state vector, so strong simulation without the presence of noise, and density matrix, which is a strong simulation in the presence of noise. And I think our maximum qubit count I've run just on my laptop is 31, but if on a system with higher memory, you can do higher. So there's a lot of also optimizations you can do in the classical simulation of these circuits, where you do a HPC kind of optimization or multi-GPU. It's a very interesting space. Oh.
I think we can take one last question, if there's more questions.
There are two questions, one this side and the other side. Which one?
You pick.
I mean, you can also chat afterward.
Yeah, well, I'll be around after. So. Okay, there it is.
So it's maybe a question that's a little bit more general, but what causes, and maybe it's just quantum effects, the performance of whatever chip to change over time? Is the state that's not visible that's changing over time, or is it the device itself that's deteriorating in some way?
Yeah, so it can be both. So when you initialize the device and you calibrate it, you set up your control wires and everything, and the entire chip has some quantum state, right? And you can experience what's called leakage, where when we came up with that idealization of the 0 and 1, there's other states that the system can access, there's two pairs or whatever. So as the system runs and as you put energy into it over the wires, you can start leaking these pairs into high energy states that, you said, no, there's only 2 states, and the device is like, oh, what? Well, I have lots of states. I don't care about your number 2. And then that's why, after running a bunch of circuits, you need to sit the device down, recalibrate it, lower it back down into its ground state. And then even worse, what can happen is, let's say your fridge breaks, and now the device is hot, and you cool it back down. You may never get it back with the initial set of calibrations you have. So it can be both an ongoing, a permanent defect, and then just the fact that when you're controlling the device, you're putting energy into it, right? You have to do that to talk to it. And this affects the state of the underlying chip. And I think in the interest of having our closing ceremony, Ray is on the staircase back there. If anybody would like to chat more after, I think we're having drinks after in the stadium. So thanks for your attention. And yeah, oh my goodness. Chateau Julia. Should I disconnect?